Hi again, Andrew Dunkley here, and thanks for joining us on Space Nuts Q&A edition. And coming up, we've got questions from Buddy about spaghettification, and I'm pretty sure he's not talking about an Italian restaurant. We're also looking at neutron stars versus black holes. I think we've had similar questions in the past, but it keeps coming up. We're also looking at wormholes, and somebody has a pre-Big Bang theory, which we'd like to discuss. We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And I do love the Q&A edition because somebody else other than us sets the agenda. The downside is we have to think. And joining me now is Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello again.
Hello again. Good afternoon. Good evening.
Good to see you. Got some interesting questions today. Do you want to get straight into it?
Yes, can do. And I will give the usual caveat right at the start of this. I'm quite happy to admit my ignorance to a lot of this. I am not a cosmologist, so this is pushing the boundaries of my knowledge to places that it has never gone before, and I'll do my very best, but my apologies. Other answers are available, and, you know, there's a film critic in the UK who often says other opinions are available, they're wrong, but they're available. In the case of this one, it may well be that other answers are available, and they are more likely to be right than mine, but I will do my best.
Fred often throws in the same caveat, so it's all good. Our first question today comes from a regular contributor. His name is Buddy.
Hello, Space Nuts. This is Buddy from Ontario, Oregon. Hey, I got a question about spaghettification. Is it an illusion, or is it real? Is it just a distortion of our eyes to the fourth dimension, or are things actually being stretched? And on that same page, they say that photons and subatomic particles act like a wave and a particle at the same time. Is that what makes it a wave, maybe? Is that a form of spaghettification? Maybe? All right. Thanks, guys. Love your podcast.
Thank you, Buddy. Buddy's always thinking. I can hear his mind from halfway across the planet just tumbling and tumbling, trying to figure out all this stuff because he comes up with so many interesting questions. Spaghettification, first part of his question is it an illusion, or, you know, if you were there, would you get spaghettified good and proper?
It's a really good question, and that thing of constantly thinking, constantly questioning everything is fundamentally what science is. You know, we find things we don't understand and we come up with ideas to explain them and try and figure it out, and there's always more to learn. So that's fabulous. In terms of spaghettification, the idea here is that if you were to fall into a black hole, it would not be pleasant. And it would be stretched out gradually so that you got stretched out like spaghetti, and it would be a very painful and unpleasant death. From the point of view of the observer looking down from above, it would also be a death that takes an incredibly long time, because there is, as you fall into a black hole, the light that's emitted is slowed down by gravity. So you get this kind of time dilation effect where somebody watching you would see your clock tick ever slower. So they get to watch your suffering in great and slow and painful detail, which is wonderful. But the idea behind spaghettification comes from the fact that if you are falling into a black hole and your feet are nearer to the black hole than your head is, your feet will experience a stronger gravitational pull. Now, this is kind of how the tides work on Earth, to be honest. It's also how the concept of the Roche limit comes about, which is where we can work out how close to a massive object like the Earth a smaller object can get before it gets torn apart. All of these things are built around the same idea, which is that the strength of the gravitational pull that you experience from a given object falls off as 1 over the distance squared. So the further away you are, the weaker the gravitational pull is. Now, if you're falling into a black hole that is a solar mass black hole, if you get a black hole the mass of the sun, it's tiny. We can actually work out the radius of that black hole. I've not got the number off the top of my head, but it's very, very small. It's probably only a few meters across, right? Yeah. A neutron star the mass of the sun will be about 2 kilometers. A black hole will be much, much smaller. What that means is that if you're falling into that, when you're getting very, very close to it, the difference in distance between your feet and your head from the middle of that is actually a significant fraction of the distance that you are from it. So if you're 2 kilometers away from this thing and you're 2 meters tall, then your feet are 1/1000th nearer than your head is. And that means that the difference in distance leads to a very big difference in gravitational pull between your feet and your head. So you will get stretched. And the closer in you get, the more dramatic that gradient is in the gravitational pull between your feet and your head. Now, you might think, okay, well, that's fine. I'll just fall in lying on my stomach. You'll still have the same problem because the difference in gravitational pull between your nose and the back of your head will be bad. So your nose will get stretched out and you'd look a bit like Pinocchio, as would other parts of your body be equally stretched out. So you're doomed either way, but it is a very real thing that would happen. The reason that you could probably argue it's an illusion is, to the best of our knowledge, we've never dropped a human into a black hole yet. So the only times you see this are in thought experiments or in expensive, high-budget Hollywood movies.
Yeah.
But the physics behind it makes sense. Now, one of the quirky outcomes of this is that as you increase the mass of a black hole, you'd increase its radius. But the force due to gravity falls off of 1/radius squared. So you have this slightly bizarre thing that you would get this happening if you were falling into a solar mass black hole or an Earth mass black hole if one existed. Supermassive black holes, though, are so incredibly big that the gradient between your feet and your head would be very small when you were near the event horizon and you wouldn't get spaghettified. So if you think about the supermassive black hole in the middle of our galaxy, the radius of that, I believe, is wider than the orbit of Neptune, 30 astronomical units.
Wow.
So if you're near the event horizon for a black hole of that size, you are something like billions of kilometers from the middle, and the distance between your feet and your head is still 2 meters. So 2 meters out of billions of kilometers is a very tiny difference. So you wouldn't really be spaghettified. So if you wanted to not be spaghettified while falling into a black hole, I'd recommend you go to the middle of the galaxy. But I would personally choose not to fall into a black hole given the choice. So I would kind of like to live.
It worked in the movie Interstellar. They managed to get into one, but yeah, that was science fiction. Although I do believe a lot of the science they developed for that film was based on actuality. They just augmented it to suit themselves. But and the second part of Buddy's question was photons. Can there be a wave and a particle at the same time?
Yeah, this is going back to the dawn of things like general relativity, special relativity, and the dawn of the 20th century, where you get this wave-particle duality concept. And it's in part based around the observed properties of light and how it behaves. And you do experiments when you do an undergrad physics degree where you reproduce what they did 120 odd years ago. And you can get both kinds of behaviors. The famous one is what's called Young's double slit experiment. So you've got a light source like the light illuminating me at the minute, and you pass that light through a wall where there are 2 very thin slits. And then you look down from above and you can see the light waves expanding away from those 2 slits and interfering with each other because they get diffracted through the gap. And you usually illustrate this, I've done this before in my undergrad teaching, by photographs of waves in the ocean passing around barriers or passing through gaps, and you see the same diffraction thing. So you've got straight waves coming towards the gap, and then they go through 2 little holes, and you get circular ripples going out that interfere with each other, and you get these interference patterns.
Yeah.
And that type of behavior is like acting as a wave. It's behaving just like waves in the ocean do. What you get, though, is if you dim your light down and dim it down and dim it down, there's a weird quantization effect that light of a given color you can't make infinitely faint because you've got a certain amount of energy carried by photons. And so if you make your light dim enough, you can isolate individual packets of energy, which is what people describe as photons. So if you get a really, 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 really faint light source, the photons, and you have them, that double slit again, the light source behind it, light going through the slit and then hitting a sensor that measures the light, you get individual flashes of light where the photons hit. And so the photons appear to be moving as packets or particles of light, and you get a single flash. If you record millions of those flashes, they will form that same diffraction pattern, So the light is behaving as both a particle and a wave at the same time. The really bizarre part of this for me is the fact that what this means is that from a probability point of view, because you get that diffraction pattern, because you get those maxima and minima, all the interference, what that means is that while light is behaving as a particle, it's technically going through both slits at once. So that particle is in two places at one time, and it all gets really, really bizarre. Ties into, again, something I was talking about in my tutorial today for my undergrad students. We were talking about something called the Yarkovsky effect, which is to do with light from the sun being absorbed by an asteroid and then re-emitted by that asteroid, and you get a transfer of momentum. If the asteroid's rotating a little bit, the direction the light is emitted is not the same as it goes in, and that means you get a little bit of a rocket thrust on the asteroid, and that can change its orbit on really long periods of time. One of my students said, I don't quite get this. How can photons which have no mass have momentum? Because you need momentum in order to transfer momentum to apply the thrust to the asteroid. So I had to look into it then, and it turns out that the concept of momentum is fundamental to photons. So these packets of energy traveling at the speed of light that have no mass still have momentum. And that momentum is entirely contained in the energy and the oscillation of the electromagnetic waves that make up that packet of energy, that particle. And it ends up going back to the famous equation E equals mc squared, which is the relationship between energy and matter. Now, E equals mc squared is a simplification of a more complex equation Einstein came up with, which, off the top of my head, I think it's E squared equals P squared C squared plus M squared C to the 4. So this is the total energy is related to the momentum times the speed of light plus the mass times the speed of light squared. So if you've got something moving very slowly, then it simplifies to E equals mc squared because there's not much momentum. But if you've got something traveling at the speed of light, the mass is 0, so the mc squared bit vanishes. And you just get the energy is equal to the momentum times the speed of light. So in other words, the momentum of a photon is equal to the energy of the photon divided by the speed of light, which means that even though photons have no mass, they still carry momentum, and it's a fundamental part of them. And what this tells you more than anything else is when you get to the quantum scale, tiny little things, when you start dealing with relativity, nothing makes sense. It's not common sense, and we're still trying to understand it, and it's all really hard. But all of that is tied into this wave-particle duality and the Young's double slit experiment. And to be honest, it makes all our heads hurt.
Yeah, it does. But great question, buddy. Thanks for sending it in.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our next question, Jonti, comes from Istok. He says, hi, I like your Space Nuts podcast. So do we. A neutron star is very dense as it contains only neutrons, so no empty space between the core and electrons, right? What happens to the matter at a black hole? Is there empty space also inside neutrons, and can they be even denser? Thank you, Istok from Slovenia. We haven't had many questions from Slovenia. Nice to hear from you. This one, I got to confess, is way out of my ballpark.
This is a really awesome question, and it's pushing the boundaries of we don't know. The way all this works, we talked about white dwarfs earlier. If you compress matter into a smaller and smaller space, you can get nuclear fusion happening, propping up a star, and that's why stars shine. A star like the sun gets to the end of its life, blows off its outer layers, can't support itself with nuclear fusion anymore because it can't get the fusion going. So gravity wins and collapses everything in. And eventually, you get to a point where atoms are propped up against each other, held up by something called electron degeneracy pressure. And what that is effectively is you've got, of a given atom, as Istok's inferring here, you've got the nucleus in the middle, and then way on the outside, you've got this cloud of electrons going around it. And those electrons are negatively charged. And the analogy people often use here is something like the nucleus is like a grape at the middle of a football field, and the electrons are like running around the boundary. So there's a lot of empty space in there, which means if you take the mass of the sun and compress it down so that all the atoms are butted up against each other, so their electron clouds are pressing on each other, and you've got rid of all the space outside the atoms, you get an object about the size of the Earth. So you take an object the mass of the sun, squash it to the size of the Earth, and at that point, the electron clouds around each atom butt up against each other, and the negative charge and the negative charge repel each other, and you get a pressure that holds it up. And that's called electron degeneracy pressure. And that works, and you can keep adding mass and adding mass, but eventually if you get to about 1.4 times the mass of the sun, a point you call the Chandrasekhar limit, the gravitational pull is strong enough to overcome the repulsion of those electrons, and gravity wins. And so things keep collapsing further. And that squashes the electrons and the protons in the atoms together, making neutrons. And so the atoms of those, well, all those atoms that made up the white dwarf, get turned into neutrons. And so suddenly you've gone from a football pitch size to a grape. Everything's squashed into the nucleus, and everything keeps collapsing. But eventually neutrons butt up against each other, and the strong nuclear force, I think it is, stops them collapsing any further. There's a new pressure which is called neutron degeneracy pressure, and that holds neutron stars up. And so you get something the mass of the sun but the size of a city, a few kilometers across.
Okay.
Keep adding mass to that, and you eventually reach critical mass. I've forgotten the name of it, but the critical mass for neutron stars is thought to be about 3 times the mass of the sun. And at that point, gravity is strong enough that the strength of the neutrons pushing apart cannot hold them up against gravity, and gravity wins. So things collapse down even further. And this is where it gets to the point of our understanding starting to fail. There are some suggestions that if you squash neutrons together with enough force, you can compress them down so that inside that neutron, you've got a lot of empty space and some subatomic particles, quarks. And you could squash them together until the force between the quarks prevents them squashing it any further, and you could get an additional kind of thing, which is where you get the concept of a quark star. And some people have speculated that within quarks, you've maybe got subatomic particles, which I think are called pions or pios or something like this. So maybe after a quark star, you can get smaller still. Fundamentally, though, every size mass scale, you'll reach a point where no force we can imagine is strong enough to hold it up, and it'll collapse further. What you get with a black hole is secondary to this. It's kind of separate to it, which is that the amount of mass you've got means that to escape from that mass within that small area, you'd have to travel faster than the speed of light. So that's where you get the event horizon of a black hole. But the physical object inside the black hole, if there is one, and we don't know if there is one, it's probably smaller than the size of that event horizon. Now, I am not an expert in this. My understanding from what I've seen written is that people think quark stars would be big enough that the gravity on their surface is low enough that light could escape. So they'd be bigger than the event horizon, so that we'd see them as physical objects. But it may be that the next step down is smaller than the event horizon, so you have a black hole. Fundamentally, what happens with the matter inside a black hole and what empty space you have inside neutrons and stuff is pushing the boundaries of our knowledge of how matter works and how particle physics works. We do think there are these subatomic particles. There's a lot of evidence for that, and that's where the idea of quark stars come from. Knowledge of what quarks are made up on is really pushing the boundaries of what we know, and I am nowhere near qualified to comment on that, other than that there is speculation that you could possibly have even smaller components that behave differently. And this is where, as we get more energetic particle colliders in the future, as we get more better telescopes, better instrumentation all around, these are the kind of questions that people want to answer as we push that boundary of knowledge back. But it's really at this point, Istok is asking questions that are at the boundaries of what our knowledge of modern physics is. And it's by asking these kind of questions that we'll learn the answers, but we're not there yet.
No, we're not. But if we didn't ask questions like this, we'd never go looking for the answers, and we'd probably stagnate as a species. So,
I mean, if you go back a long time, if we didn't ask questions, we'd probably still be sitting around saying, me wish fire hot, and not actually having the ability to have fires. And a day like today will be extremely miserable with a drizzly rain, because at least the fire that I've had on has kept me warm.
Yeah, absolutely. Thanks for the question, Istok. Lovely to hear from you. Hope all is well in Slovenia. This is Space Nuts with Andrew Dunkley and Jonti Horner.
3, 2, 1.
Space Nuts.
Our next question is an audio question, I do believe. Now, forgive me, I may have got your name wrong. I couldn't quite pick it up. Maybe it was the accent. Maybe it was just my lousy capacity to translate. But I think it's Foster.
Hello, Andrew. Hello, Fred. And hello, Jonti. I am Foster from Norway. And I have a question for you in relation to Interstellar, the movie. Probably my favorite space movie of all time. And I have a question about the wormhole and what kind of parameters theoretical has to be in order or to be in place for this to be possible. And do you ever think that we will discover or maybe use such a phenomena at some point? Thank you.
Okay. Thank you, Foster. I think that's what your name was. Norway. I was there recently, only in the last few months, and what a beautiful country you have. Got to stop in, I think, 4 or 5 different places throughout Norway. And I learned a lot about the country, Jonti, because they don't have much arable land. They've got water and they've got mountains. Yes. There's not much flat ground. It's so un-Australian, very un-Australian. And because they've got so much water, they can generate a lot of electricity, and nobody pays for electricity in Norway, from what I was told. But they don't really have much room to grow crops, and it's too cold most of the time anyway. That said, when we went to North Cape, which is the northernmost tip of Europe, which is obviously in Norway, as in north, 28 degrees it was. 28 degrees, and the locals were freaking out. That was a heat wave. To us, it was just beautiful. But one thing I did notice, and you'd probably be aware of this being from the Northern Hemisphere, their summer, where most of the population lives, their summer is not like a summer here, because they are further north than we are south, if that makes sense. So our summers can be much more severe, but their summers are very mild, very especially when you get to places like Greenland and Iceland and up in even in Canada, places like that. It's a different world.
With it, yeah. I mean, I know for a fact, having grown up in the UK, and I suspect that heat wave in Norway was brutal, that heat hits different in those countries because the buildings are engineered to keep you warm, not to keep you cool.
Correct.
And so, yeah, I'm complaining about the horrible night I had the other night with the power outage and the heat wave that we had. But it was made more bearable by the fact that the design of this house is more around keeping people cool in summer than keeping them warm in winter. Whereas when I was doing my PhD in Oxford, back in 2003, we had what was then the hottest summer on record in the UK, and now is a footnote in history because things are much warmer now than they were. Yeah. But we had a couple of days that were in the mid-30s, and I'm in this old building that is a couple of 100 years old with south-facing windows to get the light, northern hemisphere, the sun's in the south. On the ground floor, so you could only open these floor-to-ceiling windows by about an inch because they're security locked down, and no air conditioning, a lot of computers in there. It was absolutely awful. The other thing that I really notice is I'm into one where I'm 27 degrees south. The day length barely varies. When I grew up, in the winter, I'd go to school in the dark and come home in the dark. And here the day length barely varies. But we're already well off topic from the awesome question. Yes, I should say that my movie viewing over the last decade or 10 or 15 years has been much more limited thanks to how busy I've been in my career. And Interstellar has been on my to-watch list for years and never quite happened. I know it's brilliant.
You've got to do it.
And it's on the list, and I wish I'd seen it at the cinemas, but it's always been a not-today thing. It's never quite happened.
I've watched it 4 or 5 times.
Yeah.
I love it. And I think awesome. What makes it, for me, being someone in radio, is the musical score that goes with it. It is phenomenal.
It's meant to be amazing, and I'm just sad I've not got around to seeing it yet. But one of the things I know about it is that it is pretty hardcore on the science, but they did a really good job of getting some of the world's really leading theoretical physicists to give input and get really good scientific advice. And it does, to my understanding, and I say this with a bit of a caveat that I've not seen it, but my understanding talking to colleagues is it does really well what I like in good science fiction is where it gets the science right, except where it needs to get the science wrong to make the plot advance.
Exactly.
And I'm always really happy with that. I get really grumpy with films that get the science wrong to no good reason. You know, I watch films and they've got a night sky, and it's not the Earth's night sky. And it's like, you're on Earth. It is really cheap to point a camera at the sky and get a picture. Why would you make up a false night sky? There's no need for that. But if you do everything you can to get the science right, or the science to fit our best current understanding, in the case of things we've never directly experienced or seen, but you circumvent that to make the plot work, I'm totally cool with that. That's a very knowing use of science. This is all about wormholes, which are a staple of science fiction because they are a hypothetical way that we could move from one place in the universe to another at speeds much greater than the speed of light by essentially cutting out the middleman.
Yep.
And the way it's always envisaged is to envisage the universe drawn on a two-dimensional sheet of paper and then folding the sheet of paper so that two places that are nowhere near each other touch and saying, what if you could tunnel between them? Mm-hmm. Wormholes have their origins in particular solutions to the equations from Einstein's general relativity, and they are purely theoretical constructs at the minute. They're possible solutions to the model that Einstein developed that offer the possibility that you could have instantaneous travel between two distant points. There's a lot of debate over whether they are anything more than a theoretical construct. And of course, this is all predicated on the idea that Einstein's model of the universe is a correct analysis of what's actually there. And it may well be that in 50 years or 100 years, when we've got incredibly more powerful observing tools than we have now, we start to see the cracks in Einstein's model just the same way that we did with Newton's gravitation a couple of 100 years ago. There are a few variants of wormholes that have been proposed based on different solutions to those theories. Some of them have even come about kind of tied to you could potentially have a rotating black hole that would allow you to travel through the black hole without getting destroyed and use it as a tunnel to somewhere else. There are also solutions to those equations which could let you set up one of these wormholes. One of the variants of this is known as an Einstein-Rosen bridge, I believe, that could set up a permanent tunnel that could be traversable. But in order to make that work, you need material which has negative energy, which often gets talked about as exotic matter. And I've been listening to an audiobook series that's very good fun but very pulpy called Expeditionary Force, and they use wormholes all the time, and they're always talking about things made of exotic matter by technologically advanced species millions of years more advanced than we are. It's become a staple of science fiction. As to whether we will ever find them or ever be able to use them, we simply don't know yet. At the minute, they're a purely theoretical construct, so they're kind of an extreme prediction of one model of how we think the universe could work. They are possibly something that with sufficiently advanced far future technology, you could envision the ability to make them and control them. But that would require us to have technological advances beyond what we can imagine here and probably physics to work differently to how we currently understand that it would do. Yeah. I'm loath to say we couldn't do it because that strikes me as a bit like the people who in 1910 said we will never have heavier than air flight just before the Wright brothers flew. Because we don't know everything. We're in this little bubble of knowledge in an ocean of things that we don't know yet, in an ocean of darkness. And these things like wormholes are natural products of our efforts to push that boundary of knowledge further. All of this is a very long-winded way of saying, I don't have the real knowledge of how all this works. I'm not that kind of theoretical physicist. It's all very much beyond me. I greatly admire the kind of scientists that have come up with these ideas. I think they are fabulous, fabulous ideas. And if the model is correct, then wormholes could exist. You then have the leap of, could they be stable for long enough for us to ever observe them? And of course, the most important thing about a theory is it makes testable predictions. And so I'd love to see observations in the future confirm that wormholes can exist. To then have a leap beyond that to could we ever develop them and use them? I'd love to think we will do, but I think unlike the search for life elsewhere, where I think there's a chance we'll know the answer in our lifetime, I think with this, it's very unlikely we'd know the answer within our lifetime unless the answer is no. And the answer is no would come about us getting a newer model for how all these things work to explain new observations that no longer offers this as a possibility. I don't think that's going to happen, in all honesty. But yeah, it's an awesome question. I wish it was something I could be more knowledgeable about. But if you went back 400 years, it was possible for one person to have the entirety of the world's knowledge. And that's why you got these incredible polymaths who could be chemists and engineers and biologists and physicists and astronomers all at the same time.
Mm-hmm.
Nowadays, the breadth of human knowledge is so incredibly vast that nobody can be an expert in all of it. In fact, you're normally an expert in a very narrow area. And it's very fair to say that wormholes and the complexities of higher dimensional space-time and theoretical physics in that sense, and the extreme extrapolations of general relativity are way outside my wheelhouse. I'm not really qualified to say much more than that, even having done a bit of reading around it.
I like to think that fundamentally all things are possible, but I know traveling faster than light speed isn't because of the amount of energy it requires, but maybe folding space or developing wormhole technology could be the workaround. So, let's put a pin in that one for future reference when they've got it all figured out. But, wormhole technology comes up in Interstellar as created by a fourth dimension race. I won't say any more than that. But, Foster, thanks for the question. I loved it. It was terrific. And, yes, I agree with you. Probably my favourite, if at the very least in my top three science fiction films, although it's pretty close to not science fiction in many, many ways. Good on you, Foster. Thanks for the question.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, final question today comes from Rob. As I understand, the only way out of a singularity is by Hawking radiation. However, isn't the Big Bang another example? If so, then at a critical universal size, an explosion is imminent. This suggests that there were a number of singularities before the Big Bang that combined to reach critical Big Bang mass. What do you think? Could the very early black holes suggest that a number were floating around before the Big Bang and attracted mass from the Big Bang to form the galaxies? Wow, Rob, you put a lot of thought into that one.
Absolutely. And this is yet another one that gets to pushing the boundaries of any of our knowledge, to be honest. And this question from Rob is a really good illustration of where the boundaries of our knowledge when it comes to cosmology and cosmogenesis, the origin of the universe, are where science and philosophy meet. Where you start getting to the point where you are going so far beyond what we can observe and what is possible to understand with our current laws of physics, that discussion of it moves away from science and into the realms of philosophy and thinking about how we think. And the reason I say that is that our current best understanding, as I remember it from the things I've learned, is that space and time are inherently properties of the universe, which means that the question of what is before the Big Bang or the question of what's outside the universe are things that are questions of philosophy rather than science, because by definition, you can't have a before the Big Bang when time only started at the Big Bang and time is a property of the universe. Similarly, you can't have a concept of outside the universe when space is of the universe.
Yeah.
Now, as I say, this to me really gets to be philosophy rather than science because that makes my head hurt. And I think anything that makes my head hurt can be described as philosophy. Yeah. But it is, a lot of it's about how we think and how we visualize stuff. So I suspect if we got somebody on who was one of the world's leading cosmologists, they could answer this a lot more clearly, but they'd probably be saying that we can't really say anything about what was happening before the Big Bang, because before the Big Bang is a meaningless concept, because before the Big Bang time didn't exist.
Well, the question has been asked directly to us in the past, what was there before the Big Bang? And Fred's answer is always nothing. Well, no, he doesn't say nothing. He says, we don't know.
It is really a we don't know. Now, there are a number of theories out there because this verges on philosophy and religion, not in the sense of any given named faith, but rather the point at which you move from evidence and theory and prediction to faith. And I'm not myself religious, but I've got a lot of colleagues that are, and there is, despite what some people try and manufacture, there is no conflict between religion and science at all. Terry Pratchett, who I obviously put a lot of stock by because I mention him very, very often, had some really good discussions of this in the Discworld books. And the concept that, I think it's in the Science of Discworld books, that science and religion are orthogonal, in that science operates in the absence of belief because it's about evidence, whereas religion operates in the domain of outside of evidence because it's about belief. And I don't need to believe this table in front of me is there because I've got the evidence of my hands resting on it and my microphone's there. There's a lot of really interesting stuff there. And the reason that I've gone on that little bit of a detour is that questions about what happened before the Big Bang are questions that are beyond what we can beyond what we can know, because all of our ability to observe and measure is limited to the results of the Big Bang in terms of space and time. Those started at the Big Bang, so to try and understand anything about before the Big Bang with those in our current understanding of how it works becomes a matter of religion or faith, because there is no way of having evidence either way. Apologies for the bit of a background noise, by the way. The rain is pounding on the wonderful roof here, which is a very Australian experience.
I know I'm 1,000 kilometres away from you, but it just started raining here as well.
Spooky action at a distance is what that is.
Yeah, it was probably a wormhole.
Yeah, absolutely. It's teleporting through, which is why it's been so dry here recently. You're getting all the fun. Yeah, so with this question from Rob, the challenge is that you're asking the questions that we're all asking and trying to understand, but they're not questions we can really answer when it comes to things outside of the current universe. What that's led to is a number of different proposals of theoretical before the Big Bangs. One is that the Big Bang is the first thing that there ever was and will expand for forever, and that's it, and it's doom. One is that you have these Big Bangs followed by big crunches, and then you get this cyclical nature of the universe with a reset. A lot of our current theories suggest that the expansion of the universe is speeding up rather than slowing down, which argues against that. But we know in the past, and this is where it gets more to philosophy and religion and faith and complexity as well, is that in the early days of the universe, the different forces were unified, and you get phase changes in the universe as the expansion happens and the universe cools. And that's all in the very early time. But it's possible, and I've never found anyone who can explain to me that this wouldn't be possible, but it might be entirely wrong. This is Jonti speculation. Who's to say that there isn't another phase change at some point where something that we currently see as one force freezes out into two separate forces? Now, we see examples of this all over the place. It's a total hop, but when I was doing my second postdoc, I was at the Open University in the UK, and one of the conferences I went to, I met a young woman who was doing a chemistry-based degree looking at chemistry on the moon Titan. And she was interested in the availability of different chemical reactions as to whether a place like Titan, 180 degrees below freezing, could have the potential for life, given that there's liquid there in the form of liquid ethane and methane. And the standard accepted wisdom is, no, there isn't, because the more you cool down, the fewer chemical reactions are available. It just doesn't happen. But she looked at benzene, which is a compound that at room temperature, there's a single version of benzene. You have the benzene ring. What she found was that if you cool benzene down to the conditions you get on Titan, benzene forms 3 different isomers. They're all benzene, but they're different shapes of those 6 carbon atoms in a ring. At room temperature, it's got enough energy that it vibrates around and they all blur out, and you just get a single version. But you cool it down and you freeze it out to 3 distinct versions of benzene with slightly different chemistry. So suddenly by cooling it down and freezing it out, you get 3 times the availability of different chemical reactions as more chemistry can go on. And the freezing out of the forces and the breaking of them into other forces seems to be a bit like that. Now, it's way beyond my expertise and my knowledge. But this is what happens when you push really at the boundary of not just what we currently understand and we know, but what we can possibly observe. And so questions like this about the origin of the universe, about primordial black holes and where they come from, about what the conditions were before the Big Bang, even though that's meaningless, these are really at the limits of what we know and what we understand, and they're pushing beyond them. But they're also at the limits of what we believe that we could ever observe if our current models of how everything works are correct. And that's always a big caveat, because it might turn out not to be. But at the minute, the received wisdom seems to be that we can never know of something earlier than the Big Bang because that's when time and space originated. We can never know about anything outside the universe because the concept of space is you can't have an outside, because if you were outside, there would be no space and therefore you're not. Yeah, it's all a bit weird.
Unless you go down the multiverse path.
Yes, and that's what I was going to say. You get some people speculating that you can have multiple universes in parallel kind of spaces that cannot really strongly interact with each other, but where they overlap, you might see ripples in the microwave background. And so you might see some evidence in the structure of our universe about the existence of other universes that we can't ever touch, but like ripples on the surface of water are evidence of the wind. You can't see the wind, but you can see its effect.
Yeah.
So I appreciate, Rob, I've probably not got anywhere close to answering your question, but what I've done instead is explained why I can't.
Yes.
And part of that is that I'm not qualified to, I don't have the knowledge, but it's also, I think you're asking questions that fundamentally we cannot yet answer, and we may never be able to answer. And that's why these kind of discussions are fun. It's the kind of thing where you sit around a campfire and have a couple of drinks or whatever and have these deeper, meaningful discussions, because it's part of trying to understand the entirety of what there is to know.
Gotcha. Yeah, look, I'm with you there. It's how can we know? That's the question that comes to my mind when I hear a question like Rob's, which I'd love to know the answer to.
Me too.
How can we possibly know? It's what was before the Big Bang? What's outside the universe? They're all just impossible.
But even beyond that, even if we could get an answer, would we be able to understand it? It may well seem that there are answers to this that are there, but are so far beyond us at the minute that we don't even have the framework to formulate those answers.
Correct. All right. Rob, thanks for your question. Lovely to hear from you. Thanks to everyone who contributed to this week's Q&A session. If you would like to do so, jump on our website, spacenuts.io, and click on the AMA link at the top. And you can send us a text question by giving us your name, your email address, and putting your message in there. Don't forget to tell us who you are or where you're from. But if you scroll down a bit, there's the start recording button. If you've got a device with a microphone, like a smartphone, or most computers these days, particularly laptops and MacBooks and things like that, you can send us an audio question. We'd love to get some of those as well. So please send them in to us and have a look around on our website while you're there. And don't forget social media. We've got a strong presence on Facebook and Instagram, and the group that was created by Space Nuts listeners, the Space Nuts podcast group on Facebook. Very much worthwhile joining that group and talking amongst each other and solving all the problems of the universe, including Rob's probably. Check it out. Just do a search for Space Nuts on Facebook or Space Nuts Podcast Group. They're both there. Both have thousands upon thousands of followers. So it's fantastic. Love it. And Jonti, we are done. Thank you so much for tackling all of that. They were some pretty curly questions, especially the spaghetti one. Lots of curls in that.
Make me hungry as well.
Yes. I had spaghetti for dinner earlier, in fact. We'll catch you next time. Jonti, thank you so much.
It's a pleasure. Thank you. And awesome questions. Really enjoyed it, even if my head now hurts.
You can take something for that. And thank you for listening. Don't forget to, as I said, send your questions in via our website. And thanks to Hugh in the studio, who couldn't be with us today because he and his wife were having a big night out, which is terrific, and they deserve it. And from me, Andrew Dunkley, thanks for your company. Catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.